For fieldwork exercise number 6, we will do a trigonometric leveling. For introduction, double-rotted differential leveling is a method of determining the difference in elevation between points by employing two roots simultaneously. Two turning points are established at each setup of the leveling instrument. Two sets of independent backsides and foresides are taken. Employing double-rotted differential leveling provide a continuous check on the process of determining ground elevations while the work is in progress. The method is also useful when there is an urgent need to undertake differential leveling in a short period of time, where no established benchmarks are available for checking the results. The objectives in doing the trigonometric leveling first is to acquire and develop the skills of determining the vertical distance, which is the elevation and the height of a remote point by applying trigonometric and related analysis. Second, to develop the skills of reading vertical angles using theodolite or the total station. In doing this fieldwork, the instrument or the accessories to use are theodolite, leveling rod, markers, either chalk or marking pins, measuring tape, plumb bob, and wrench pole. In doing this fieldwork, the surveyor must set up the theodolite at a convenient location and call it point A. In such location, the leveling rod, the theodolite, and the remote point must be visible. At the same point, use a telescope to take sight at the topmost remote point, then read it as a vertical angle and mark it as an angle alpha. In order to determine the precision of the observation, take another sight for the second trial, and then calculate the mean of the two vertical angles or the angle of elevation of the specified point from the first station. To determine the height of the instrument of the station A and the coming station B, we need to set up the leveling staff or rod vertically near the base of the remote point and take the level foresight. For the second station, transfer the instrument level, which is the theodolite, towards the location of the remote point and designate it as station B. Then measure its distance by the taping from its initial position, which is the station A, so that we can determine the distance of the station A to station B. Just like at the station A, we also need to take sight at the topmost remote point of the station B for the vertical angle and then record it as an angle beta. Then repeat it for the second trial. Then calculate the mean. Then level the telescope while at B and get the height of the instrument by sighting the same leveling rod near the base of the remote point. After finishing this fieldwork, we can now notice the right triangles formed, and it is to determine the height of the remote point. This fieldwork will not consider the effects of the combined correction of Earth's curvature and refraction. To determine the difference in elevation between two instrument setups, the equation is the difference in height of instrument is equals to height of the first station minus height of the second station. To determine the angle beta, we have to use the tangent function. But we also consider triangle BEF to solve the distance x, which is the distance B to E. The equation is tangent beta is equals to height of the first station minus height of the second station all over x. For the analysis of the oblique triangle AFD, we have first to solve the segment AF. To solve it, we have to determine the sum of distance AB and distance x. The equation is segment AF is equals to AB plus x. To determine the distance FD, we have to consider the triangle AFD and use sine law. The equation is AB plus X all over sine beta minus alpha is equals to FD all over sine alpha. To determine the height of the remote point PG, we have to consider triangle FDG. The equation is sine beta is equals to height of the remote point minus height of the first station all over FD.